2.1. Functions of acute angles. Oh, does anybody still not have a textbook? Good, good. Oh, did a hand go up and then back down? Because they're here at the school. If you do not have a textbook, you guys got to get one, okay? All right, so the big difference from chapter 1 to chapter 2. Chapter 1 was all about putting the triangle on the coordinate plane. So the first thing we would do is we would draw the coordinate plane. You know, I would draw this triangle. We would label the X side, the Y side. I just realized, was I muted that whole time?
No.
Nothing.
No, I hear.
No,
Okay.
it like cut out.
It just cut out? Okay. So we talked about, I said the big difference between chapter 1 and chapter 2. Chapter 1 was all about having the triangle on the coordinate plane. We labeled the sides X, Y, and R. But in order for us to actually apply trigonometry into the real world, we're going to have to take this triangle and pull it off the coordinate plane. Okay? So when I take this triangle and I pull it off the coordinate plane, you know, there's no way, I know the hypotenuse is still across from the right angle, but I don't know which of these are X and Y. Okay? We don't know that anymore, right? Like, did I take the triangle, pull it off, and flip it? You don't know that. So, we're not sure what X and Y are anymore. So we're now going to have to label stuff a little differently. And we've got a saying for that. It's called SOHCAHTOA. SOHCAHTOA. Okay? And I'll just tell you what that means here in a little bit. So if I wanted to find this angle right here, we used to call this the Y side, but now, based upon the angle that we're looking at, we're going to call this the opposite side. This used to be the X side of the triangle. Well, now we're going to call this the adjacent side. Adjacent is a word from geometry. You guys should know. It means touching or sharing. This up here is still the hypotenuse. So all we're doing is we're renaming the triangle based on the angle that you're looking at, the opposite, the adjacent, and the hypotenuse. Okay? So I'm going to write my 6 trig functions. Sine of theta, cosine of theta, tangent of theta. Their reciprocals, cosecant of theta, secant of theta, cotangent of theta. Am I going too fast?
No, you're good.
The old way that we used to think about sine was y over r. The new way that we're going to think about sine, and this is why this little saying SOHCAHTOA is so important. SOHCAHTOA stands for sine is opposite over hypotenuse. Cosine, we used to think about as x over r. Now we're going to think about cosine in terms of adjacent over hypotenuse. Tangent, we used to think about in terms of y over x. We're now going to think about tangent in terms of opposite over adjacent. Okay, and if you go back to this picture, If I'm looking at that angle right there, sine, which is y, but it's also the opposite side over the hypotenuse, which is r. Cosine is the adjacent over the hypotenuse. Tangent is the opposite leg over the adjacent leg. So nothing has changed mathematically. We're just naming things differently so that when I pull the triangle off the coordinate plane, x and y and r aren't there anymore. And then once I know these three, the reciprocals, again, you just flip. So cosecant works out to be the hypotenuse over the opposite. Secant is the hypotenuse over the adjacent. And cotangent is adjacent over opposite. And that is the big blue box on page 46. So we're just showing you where all that comes from, okay? Issues, concerns on our new way of thinking about or looking at our trig functions.
What is like SOHCAHTOA stand for, like the whole thing?
SOHCAHTOA stands for sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So usually for like the first month after I teach SOHCAHTOA, every time I hand a test or a quiz out to the students, they would write SOHCAHTOA on the top of their test paper because it tells them right away sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Okay? All right, so let's look at example 1. Example 1, there's a picture, so I'm going to draw the picture. It's a right triangle. Can't see it. Sorry, guys. It shows that this side is 25, this side is 24, this side is 7, C, B, A. They want us to find sine, cosine, and tangent for angles A and angle B, okay? So based on this picture, they want me to find sine of angle A, cosine of angle A, tangent of angle A. They then also want me to find sine of angle B, cosine of angle B, and tangent of angle B. All right.
Mr. Butt,
Yeah.
I have to leave because I have an appointment.
Okay. No problem. All right. So when you're answering these trig questions, it's all about perspective. It's all about where you're coming from. So for these first three, I'm focused on angle A. So up here in your triangle, I'm focused on angle A. So based on this angle A, if I want to find what sine is, well, I know sine is the opposite leg, which in this case, the opposite leg is 7, over the hypotenuse, which is 25. And that's the answer. Sine of angle A for this particular triangle is 7 over 25. Cosine of angle A is now the adjacent leg, which is 24, over the hypotenuse, which is 25. And then tangent for angle A. Tangent is the opposite leg, which is 7, over the adjacent leg, which is 24. Anybody have a question on those? It's really not that hard, right? This is a two-part question, though. They want me to also figure out sine, cosine, and tangent from angle B. So the same triangle, I'm now just going to focus my attention on angle B. So based on, if I'm looking from angle B, sine of angle B, so from this position, now the opposite leg is 24. The hypotenuse is 25.
Mr. Bet,
Yeah.
if you look in the chat, Colin like can't see anything. He said it's like blurry.
Oh. Let me see if I can call the chat up. Let's see. Doing it's extremely blurry. Oh, okay. Is it blurry for all you guys?
It's a little blurry for me, but I can make it out though.
A little bit.
Slightly blurry.
All right. I can't see my own camera, so let me end the meeting, and I will come back in about 3 minutes. Let me monkey with my camera and see if I can get it a little bit clearer. Okay. So,
Okay.
see you guys in about 3 minutes. Bye. The hypotenuse is the only piece that does not change. Now we're finding our three trig functions based upon coming at the triangle from angle B. So based on angle B, now this is my opposite leg, still my hypotenuse, so opposite over hypotenuse. Cosine is the adjacent leg, so looking at this from angle B, the adjacent leg is the 7 over the hypotenuse, which is 25. And then finally, looking at it from tangent, the opposite is 24 over the adjacent, which is 7. Okay? Something kind of neat happens when you do this. You realize that the answers for sine and cosine, they just switch, right? The opposite leg from this angle is the adjacent leg from this angle. Vice versa, the opposite leg from this angle is the adjacent leg from this angle. So if you attack the triangle from a different angle, the sine and cosine answer just switches. Always. Make sense? And that's what it shows on the top of the next page. So if you look over on the top of page 47, our next terminology that we're going to come across is called cofunctions. It says in that paragraph that you may have noticed that sine of angle A and cosine of angle B, or cosine of angle A and sine of angle B, were the same. And again, that has to be true for any triangle. The sine of the one answer is cosine of the other answer, okay? But the deeper meaning behind it is when we have this triangle, so I'll draw you just a quick right triangle here. You know, this is my 90-degree angle, so obviously this is my hypotenuse. I'm just going to make up, you know, any two other answers. I'm going to say that this is a 40-degree angle. So you guys know that there's 180 degrees. So then this one has to be 50 degrees. So what's important about this is for any triangle, if I tell you that, you know, sine of 40 degrees would have to equal cosine from the other angle of 50 degrees. Right? Sine, which is opposite over hypotenuse, would have to be the same as cosine, which is adjacent over hypotenuse. That works true for any triangle as long as those two angles add up to 90 degrees. Okay? So if you look at the big blue box in the almost 2/3 of the way down on page 47, you know, we'll get into the mathy mumbo jumbo of it, so I'll let you guys copy these down. They're called cofunction identities. So copy these 6. I'm going to copy them as well. We'll come back here in a minute. We'll talk about them. All right, so if we talk about these, you realize the whole triangle has 180 degrees. Everything we're dealing with has to be a right triangle right now because we have to be able to use Pythagorean theorem. So if you know that a triangle is 180 degrees, but you subtract the right angle, what you are dealing with is 90 degrees left in every triangle. So when I made this this real right triangle up here and I threw a 40 in here, that's how I real quick said, oh, there's 50 degrees left. These two angles have to make up the other 90 degrees. So in order for you to be talking about the same triangle, if I'm telling you for some triangle, here's your 90-degree angle. If I call this angle A, in order for us to be talking about this other angle up here, remember, together they equal 90 degrees. So this other angle up here has to be the 90 degrees minus whatever angle A is. So in that blue box, when they keep referring to this angle as 90 minus A, 90 minus A, 90 minus A, 90 minus A is the other angle in the top. Does that make sense? Nobody. I'll take that as a yes. Good talk, guys. So let's look at example 2. Example 2 has an A, a B, and a C. A is cosine of 52 degrees. B is tangent of 71 degrees. And C is secant of 24 degrees. And our directions are find the co-function. Again, another word to add to your vocabulary for trig. Co-functions, okay? All right, again, I'm going to do this the long, painful way. So when you're saying, do I have to do it this way? No, but I'm showing you this because if it gets algebraic, this is how you're going to want to do it. So I know that the co-function for cosine is sine. So sine equals cosine of 90 minus I'm sorry, scratch that. I did that wrong. I know what cosine is. My bad. I don't know what sine is. So cosine of angle A equals sine of 90 minus angle A. Oh, I'm off the paper. So I'm using cosine to find sine. When I plug that angle in, cosine of 52 degrees equals sine of 90 minus 52 degrees. So the co-function, cosine of 52 degrees, is the same as sine of 38 degrees. That's the answer. So what is the co-function for cosine of 52? Sine of 38. Which again, if somebody's saying, couldn't I just do 90 minus 52 right off the bat and get that answer? Yes, you can, okay? But I'm just warning you, eventually you could have an algebra expression for the angle, and then it gets to be a little trickier, which we'll get to some of those in a little bit, okay? I'm trying for part B to find the co-function for tangent. So I know tangent of 71 equals the co-function for tangent is cotangent of 90 minus 71. I kind of skipped the whole A part and just went right to the angles. So therefore, the co-function for tangent of 71 is cotangent of 19. Issues, concerns, easy. Last, jump down here, I'm running out of space. The cofunction for secant. So secant of 24 equals the cofunction for secant is cosecant. And again, it's of 90 minus the angle, which in this case is 24. Apologize, I'm running out of space here on my paper. So I get an answer of cosecant 90 minus 24 is 66 degrees. Questions, issues, concerns? All right. Example 3. So I'm telling you guys, when we do these triangles, sine and cosine very, very, very rarely equal each other. Okay? So, we talked about our quadrantal angles. So this angle would open at 0 degrees. Well, at 0 degrees, you've got, you have an x value, but you don't have a y value. And then as this angle opens, it's going up, so y is getting bigger and bigger and bigger. But as this angle is opening, we're robbing from x to make all these little triangles, right? So as y is opening and getting bigger and bigger and bigger, we know x is getting smaller and smaller and smaller. Okay? So there's only one time in this entire triangle where these two legs are actually equal to each other. All right? So that's what I'm saying. Sine and cosine don't ever equal each other that often. Does that make sense? Like usually your triangle is longer than it is tall, so it has a bigger x value. Or, it's taller than it is wide, so it has a bigger y value. So when we look at example 3, there's an A and a B. So example 3a says cosine of theta plus 4 equals sine of 3 theta plus 2. So star this because this is something that doesn't happen often. If you're saying to yourself, you're always supposed to try and make the connection in trig of how am I connecting these two trig functions? Sine is comparing the x value. Y is looking at the y value. So it doesn't happen often, but in this particular case, these are equal to each other. The only time that sine can ever equal cosine, if you go back to those last previous notes that we talked about, the only time that sine can ever equal cosine is if the two angles together equal 90 degrees. That's the whole definition behind cofunctions. So if you're looking at an equation and it says sine equals cosine, the only way that that's possible is if the angles are complements of each other. So theta plus 4 plus 3 theta plus 2 would have to equal 90 degrees. Does that make sense?
Yes.
Good. And now it just turns into an algebra 1 problem. 1 theta plus 3 more theta gives you 4 theta. Plus 6 equals 90. So 4 theta equals, subtract that over, you get 94. Divide by 4. 94. I can't do math. 84. and you get theta equals 21. Part B, they say tangent of 2 theta minus 18 equals cotangent of theta plus 18. So again, if you're looking at this question B, you're saying to yourself tangent equals cotangent. That's weird because we know tangent and cotangent's relationship is that they're reciprocals of each other. So again, I'm going to say to you, this doesn't happen often. The only way that tangent equals cotangent is if we're in the same triangle, which once again means that their angles have to be complements of each other. So 2 theta minus 18 plus theta plus 18 would have to equal 90 degrees. Two theta plus another theta gives you 3 theta. The positive and negative 18 cancel out. Divide by 3, and you get theta equals 30. Okay? So again, keep these in front of you as you're doing the homework. If we are telling you that sine equals cosine, or cosine equals sine, or secant equals cosecant, if we're telling you that these things are equal to each other, that's cofunctions, and that only exists when we're in the same triangle. And that means that those other two angles in the triangle must add up to 90 degrees. Okay? All right. So there's some notes about before we get to example 2, but we've already talked about these. They're telling you that, as an angle grows, the y value gets bigger and the x value gets smaller. So we're doing that comparison again for example 4. And we're looking at we're determining it's true or false. Is sine of 21 degrees greater than sine of 18 degrees? That's what A is. And B, they want to know cosine of 49 degrees less than or equal to cosine of 56 degrees. Okay? So there is your example for A and B. I'll let you copy those. All right, so I'm going to just move my paper down here for a second. We already know that as this angle rotates, as this opens up, y starts with 0 value and gets bigger as the angle gets bigger. So as the angle gets bigger, y gets bigger. Sine is controlled by y. So as the angle gets bigger, sine gets bigger. So is sine of 21 greater than sine of 18? Yes, it is. This is true. The only way that y can get bigger, it has to rob from somebody. So as y is increasing, we know this x value is decreasing. So as the angle gets bigger, x gets smaller. So the bigger the value, the smaller the x. So is cosine of 56 more than cosine of 49? No, it is not. This one is false. Does that make sense? Bigger the angle, bigger the y. Smaller the angle, bigger the x. Okay?
Can you explain it again?
Sure. So when we start with a 0 degree angle, 0 degrees is laying perfectly flat on that x-axis. So that means it has no y value. As the angle increases, or as this angle is getting bigger, y is getting bigger. Okay? So, I mean, think about it. If I draw like a 5-degree angle, a 5-degree angle would be this little skinny angle like that. You would have a really small y value. But if I draw like a 45-degree angle, 45-degree angle has a much bigger y value, right? If I draw an 89-degree angle, we're almost perfectly straight up and down. An 89-degree angle has like the biggest y value ever. So as this angle is opening up, in order to get taller, y has to get bigger. So that's why the bigger the angle, the bigger the sine value, because sine is controlled by y. Vice versa, though, in order for this to open up and get taller and taller and taller and taller, we are stealing from x. So as this angle is getting bigger, if you notice, these x values are getting smaller. Well, cosine is controlled by x. So as the angle gets bigger, cosine actually gets smaller. So cosine of 56 is smaller than cosine of 49. That's why this one's false. Okay?
Okay.
All right. Last thing we're talking about is our special right triangles. You should have done these in geometry. Hopefully you memorized these in geometry, but that was 6 months ago, so I'll assume you did or didn't. Can anybody name my two special right triangles?
You can assume we didn't.
All right, I'll assume nothing. So your two special right triangles are the, so let me write this down first. Two special right triangles. The first one is the 45, 40, oops, first one is the 45, 45, 90. And then the second one is the 30, 60, 90. Draw a picture to go with them. These numbers are obviously corresponding to their angles. So you've got a right triangle where the two angles are 45 and 45. These two angles are the same, so this is actually an isosceles right triangle. Which means if their two sides are the same, or I'm sorry, if their two angles are the same, well then their two legs are the same also. And because we can pick any number here that we want to work with, let's pick something really, really nice. I'm going to pick 1. So if these two angles are 45, I'm going to say that that's 1 and that's 1. And all I need to do now is figure out the hypotenuse. Okay? So to figure out the hypotenuse, it's leg squared plus leg squared equals hypotenuse squared. 1 squared is 1. 1 squared is 1. So you end up getting 2. Square root both sides. So the hypotenuse is the square root of 2. So, do we remember seeing this last year in geometry?
Yes.
Yeah.
So you should memorize the ratio. When you have a 45, 45, 90 triangle, we memorize this as the 1, 1 square root of 2. And then there's only two things you have to do. You realize that the legs have to be equal. So you're either going from a leg to the hypotenuse, or you're going from the hypotenuse back to the leg. So if I was nice enough to give you the leg, what would you multiply 1 by to get to the square root of 2? The leg to the hypotenuse, all you do is multiply by the square root of 2. If I give you the hypotenuse and you want to go back to the leg, all you do is divide by the square root of 2. So let me give you a homemade example of that before we move on. So if I give you this triangle, I'm going to tell you that it's a 45, 45, 90. And I give you that the hypotenuse is 3 square roots of, I don't know, 3 square roots of 3. You guys find the other 2 legs. Take 30 seconds. We got answers? Nobody has any answers. Lauren, what'd you get?
3 square root 6 over 2.
3 square roots of 6 over 2. Let's see if she's right. All right. So you identify that they gave you the hypotenuse. So to find the leg, to go from the hypotenuse back to the leg, we're just going to divide by the square root of 2. So that means that this is 3 square roots of 3 over the square root of 2. She rationalizes it, and she gets 3. This is going to give her another. Why did I put that? She's going to get 3 square roots of 6 over 2. And obviously, the 2 legs, the ratio of the legs is that they're the same. So if one leg is 3 square roots of 6 over 2, the other leg is the same. Very nice, Lauren. Good job. Okay. Our second special right triangle that we're going to memorize is the 30, 60, 90 triangle. So the second one, we get another piece of paper. Well, let's first show you where this comes from. So I'm going to start out with an equilateral triangle. An equilateral triangle would be if all the angles were 60. Okay? If all of the angles are the same, I also know that all of the sides are the same. Okay? So I can pick any number that I want for the sides because, again, all we're worried about is the ratio. So if you're sitting there saying, like, how did he know to pick 1? I didn't have to pick 1. I could have picked any number that I want. I could have picked 5. I could have picked 10. Because you realize whatever ratio you pick, eventually you're going to reduce it down. So if you pick a number that's too big, it's fine. You're just going to reduce it down. Okay? That's why I always pick nice numbers. Now, I'm telling you that in order to get the 30, 60, 90 triangle, all these angles are 60 to start in an equilateral triangle. Well, in order to get 30, I'm going to have to cut one of them in half. So that's exactly what we're going to do. We're going to take this triangle, and we're going to split it exactly in half. Okay? By doing that, there's the 90-degree angle that I need, and there's the 30-degree angle that I need. Okay? So I'm going to redraw half my triangle. There's my 90, there's my 60, and there's my 30. Okay? Now, because I cut the triangle in half, normally I like to start with the number 1. But I don't want to cut 1 in half and make a fraction if I don't have to. So because I know that I took this big triangle and I cut it in half, let's start with all the sides equaling 2. Now when I cut this in half, this piece that's 2 is still 2. I cut the base in half, so this down here is 1. So now the only piece of the triangle that I don't know is I don't know this side over here. I don't know the leg across from the 60-degree angle. Okay? So we're going to do Pythagorean theorem. I do know one leg squared plus, I don't know the other leg squared, equals hypotenuse squared. So I get 1 plus x squared equals 4. Subtract that over. I get x squared equals 3. Square root, and I get x equals the square root of 3. And this is now the ratio that you need to memorize for the 30, 60, 90 triangle. The 30, 60, 90 triangle is the 1, 2, square root of 3. Okay? Now, the other triangle was a lot easier. You knew the legs had to be the same. So all you could be asked was, how do I use a leg to find the hypotenuse? Or how do I use the hypotenuse to go back to the leg? There was only one jump you had to make. Okay? Whereas here, my legs aren't the same. All right? So what we're going to do is we're going to classify these as the one that it has the value of 1. We're going to call that the short leg. The square root of 3, I'm going to call that the long leg. The 2, still the hypotenuse. So now my numbers up here are 1, 2, and the square root of 3. Again, I want to keep things simple. The easiest number for me to work with in math is this 1. So this triangle all revolves around knowing the short leg. So if you know the short leg, that's great. If you don't know the short leg, the first thing you want to do is you want to find the short leg. Okay? Because once I know the short leg, if I want to go from the short leg to the long leg, how do I turn a 1 into a square root of 3? You times it by the square root of 3. If I want to use the short leg to find the hypotenuse, how do I turn a 1 into a 2? You times it by 2. And then vice versa, if I want to actually find the short leg first, if they give me the long leg and I want to find the short leg, divide by the square root of 3. If they give me the hypotenuse and I want to find the short leg, divide by 2. We remember seeing this one last year now in geometry.
Yes.
Were you made to memorize it?
I think so, but I don't remember it anymore.
6 months, a long time ago. All right, so let me give you an example dealing with this triangle. So I give you that this piece of the triangle is 3 square roots of 2. Find that side, find that side. Take 5.
Shouldn't the 30 be on the top?
It can be anywhere. I can take the triangle and just flip it over.
Oh, okay.
Okay. So this is a great question. So you know the short leg has to be across from the small angle. So for this particular problem, that means A is your short leg. Okay. We got answers? What do we got, Megan?
Sorry.
No, that's okay. Anybody want to help her out? Go ahead, Lewis.
The hypotenuse is 2 times the square root of 6, and the short leg is the square root of 6.
Okay, let's see if Lewis is right. Here we go. So again, a lot of trig is all about you understanding, what is the information that they gave us and how are we going to connect that to what we're trying to find. Okay, so I keep saying that over and over again, like with the Pythagorean identities, I can use sine to find cosine, or, with the reciprocal identities, I can use sine to find cosecant. We learned today about your cofunctional identities. So again, it's all about making the connections between the information. So I'm trying to solve this whole triangle. So first thing I need to do is understand we were given the side across from the 60-degree angle. So we were given the long leg. I know that I want to find the short leg first, okay? Short leg will make life easy because the short leg is 1. So to go from the long leg to the short leg, so 3 square root of 2. Again, we've got the notes above it here. To go from the long leg back to the short leg, all you need to do is divide by the square root of, divide by the square root of 3. We're going to rationalize it. And we end up getting 3 square roots of 6 over 3, which reduces nicely. So I agree, the short leg is the square root of 6. And then once we have the short leg, to go from the short leg to the hypotenuse, all we need to do is times it by 2. So the square root of 6 times 2 is 2 square root of 6. Lewis, very nice. The goal eventually, guys, will you be able to do that almost mentally in about a week or so, hopefully, okay? You guys want to see any more of those, or we think we got it?
We got it.
We got it. Example 5, and we are done. Example 5, they want us to find all 6 trig functions for a 60-degree angle. So, example 5, find all 6 trig functions for 60-degree angle. Oh, sorry. All right. So again, I'm a visual person. First thing I'm going to do, remember we have now moved off of the coordinate plane. I'm going to draw myself a triangle. Okay. Everything has to be a right triangle right now. So throw your 60-degree angle in there. The whole point of this problem is I'm trying to find a 60-degree angle. So make one of your angles 60 degrees. By default, the other one then is 30 degrees. So there's the picture that I get. And look at that. It's one of the 2 special triangles that we just talked about. A 30, 60, 90 we have memorized. I know that the short leg is across from the short angle. So it's 1. The other long leg is across from the 60-degree angle, which is root 3. The hypotenuse is 2. Which again, the quicker you memorize these, the quicker it's going to make life easy. They now want me to find all 6 trig functions based on this angle up here. So I want to find sine of 60 degrees, cosine of 60 degrees, tangent of 60 degrees, and then their reciprocals, cosecant of 60 degrees, secant of 60 degrees, cotangent of 60 degrees. Okay. Based on up here, again, we're not thinking of this in terms of x's and y's and r's anymore because this triangle is clearly pulled off the coordinate plane. We're now thinking in terms of SOHCAHTOA. So I'm thinking of sine in terms of the opposite leg over the hypotenuse. So based on this 60-degree angle, the opposite leg is the square root of 3. The hypotenuse is over 2. Cosine. Cosine is the adjacent leg. So from this 60-degree angle, the adjacent leg is the 1 over the hypotenuse, which is 2. Tangent is the opposite leg over the adjacent leg, which is the square root of 3 over 1, which is just the square root of 3. And then as long as you can find those 3, you guys should know the last 3 are just their reciprocals. So cosecant is 2 over the square root of 3, secant is 2, and tangent is 1 over the square root of 3. I'm going to rationalize these, and you get 2 square roots of 3 over 3, and the square root of 3 over 3. Okay? Anybody have any questions or any issues that you can think of on 2.1 as of right now? Otherwise, the assignment's up on the assignments page. You guys can go to work, and I'll see you tomorrow. All right.